Imagine diving into absolute darkness. You're plunging into water that is literally colder than freezing.
Right, which sounds impossible, but yeah.
Yeah, exactly. And you are hundreds of meters below this solid ceiling of ice that just stretches for miles in every direction.
There's no popping up for a quick breath.
No surface at all. And your heart slows to a crawl down to like one single beat every 6 seconds. Your muscles are black, literally black, because they're packed with so much oxygen they look like bruised meat.
It's an incredibly intense visual.
You are a weddell seal, and you are surviving in a place that, by all conventional laws of biology, really should have killed you an hour ago.
It really is the ultimate extreme. I mean, we tend to look at a map of Antarctica and just see this blank white space.
A sterile wasteland.
Exactly, this empty environment where life is just impossible. But the reality when you actually get into the data is that this continent is a canvas for some of the most sophisticated, just mind-bending biological adaptations on the planet.
And if you've ever looked at that map and thought it was just a barren wasteland, well, we are going to completely shatter that misconception for you today. We are taking a deep dive into an incredible stack of research today. We've got papers, marine biology studies, documentary transcripts, stuff like biodiversity and ecosystems of Antarctica, the frozen edge, all of it.
Really fascinating source material.
Oh, it's wild. And our mission for this deep dive is to explore the biological engineering, the high-stakes seasonal timing, and basically the absolute limits of survival. But let's just set the physical stage for a second here.
Yeah, we have to talk about the physical environment first.
Right, because we are talking about a continent where 98% of the landmass is covered in ice. And not just a thin sheet of ice. I mean, ice up to 4.7 kilometers thick.
That's nearly 3 miles of solid ice.
And the temperatures, they plunge to minus 89.4 degrees Celsius, which for our Fahrenheit listeners, that is minus 128.9 degrees.
Which is, I mean, just to put that temperature into perspective for you, boiling water thrown into the air there freezes into crystals before it even hits the ground.
Wow.
Yeah, exposed human skin freezes in less than a minute. Structural steel can actually become brittle and shatter. And compounding all of that temperature is the wind.
The katabatic storm.
Yeah, exactly, the katabatic winds. So these are driven entirely by gravity. You have this massive high-altitude dome of ice in the very center of the continent, right?
Right.
And the air above it gets super cooled, making it incredibly dense and just physically heavy.
So it basically just slides off.
That dense air literally falls down the slopes of the ice sheet toward the coast, and it accelerates as it goes. It creates these sustained freezing winds that can easily exceed 300 kilometers per hour.
Which is faster than a Category 5 hurricane.
Easily.
Yeah.
It is an environment that is actively hostile to life as we conventionally understand it.
Which means surviving here isn't just a matter of, putting on a thicker biological winter coat. You can't just grow more fur and wait it out. Surviving in Antarctica is like this perfectly choreographed, high-stakes dance with the closing door.
That's a great way to put it.
You make one wrong step, you miss your cue by a single week, or your internal thermostat malfunctions by a single degree, and that door just slams shut. You're done.
Right, because what you're looking at here are extremophiles.
Right, extremophiles.
Organisms that thrive in physically or geochemically extreme conditions that are, well, detrimental to most life on Earth. But more than just enduring the cold, this entire ecosystem relies on an exquisite rhythm.
Timing is everything.
It's a world governed by strict seasonal timing. The organisms here have adaptations that completely rewrite our understanding of biology, of physical limits, and honestly, of intelligence.
We're going to take you from those howling surface storms all the way down into pitch black lakes buried under miles of ice. But let's start at the most punishing place imaginable.
The surface of the ice, in the absolute dead of winter.
Because out there, survival actually begins with community.
The emperor penguin. It's an animal that essentially looks at everything biology dictates about migration and does the exact opposite.
Right, because most animals, when winter approaches, they flee the cold. They head for the equator, they go to where the food and the warmth are. But emperor penguins, they march up to 100 kilometers inland.
Away from the relatively warmer ocean.
Away from the ocean, onto solid sea ice, just to breed during the darkest, coldest months of the year. I mean, why march into the apocalypse?
Well, it really comes down to the physics of the seasons and the biological demands of their chicks. By breeding on that thick, stable sea ice during the dead of winter, they're essentially setting a timer.
Okay, a timer for what?
For when the chicks finally hatch and grow large enough to require massive, continuous amounts of food. By that point, the season has turned. the sea ice begins to break up, bringing the open ocean and its entire summer bounty of food right to their doorstep exactly when those chicks need it most.
Oh, wow. So they endure the worst possible conditions so their offspring can be born into the best possible conditions.
Exactly. But the physical toll is just staggering.
Yeah, the sources talk about this. After the female lays a single egg, she is completely depleted, so she leaves and walks all the way back to the ocean to feed.
Leaving the male behind.
Right. The male is left balancing this single egg on his feet, tucked under a warm fold of skin, the brood pouch, and he just stands there for 2 months.
In total darkness.
In total darkness without eating a single thing.
And if that male slips or gets bumped and that egg touches the raw ice, the embryo inside will die in a matter of minutes.
Just minutes.
The thermal drain of the ice is absolute. So he stands there motionless, starving, basically holding the next generation on his toes.
But structurally, how is this bird not just freezing into a solid block of ice? We're talking about minus 60-degree winds.
The physical adaptations are marvels of thermodynamic engineering, honestly. Let's start with the exterior. They have 4 overlapping layers of densely packed, oiled feathers.
And most birds have feathers for flight, but these are practically armor.
They really are. The feathers are extremely short and stiff, and they pack together at an incredible density. We're talking up to 15 feathers per square centimeter.
That is dense.
And they are heavily coated in an oil secreted by a gland near their tail, which makes them entirely wind and waterproof. But more importantly, this interlocking matrix traps a microscopic layer of air right against the skin.
And air is a terrible conductor of heat.
Right, which makes it an exceptional insulator. The wind simply cannot penetrate that matrix to strip the heat away. And beneath that, there is a thick, vascularized layer of blubber for both insulation and energy reserves.
Okay, so the blubber and the feathers, that makes sense. But what about the feet? Because they are standing on solid ice for 2 months. How do their feet not get frostbite, turn black, and just snap off?
Now, that requires a physiological mechanism called a countercurrent heat exchange system. It is an elegant solution to a massive plumbing problem.
A plumbing problem. Okay, explain that.
Well, in a normal extremity, you have arteries pumping hot blood from the core down to the toes, and veins pumping cold blood from the toes back to the core. If a penguin had a normal vascular system, it would constantly be pumping 60 degrees of its core body heat directly into the ice.
Oh, just bleeding thermal energy until it died.
Exactly. So how do they stop the heat loss? By redesigning the plumbing. In the penguin's legs, the arteries carrying the warm blood down to the feet are wrapped tightly around the veins carrying the cold blood back up.
Wait, wrapped around each other?
Yes. So as the warm blood travels down, the heat physically diffuses across the blood vessel walls directly into the returning cold blood.
The heat jumps ship before it ever reaches the feet.
It's a thermal recycling loop. By the time the arterial blood reaches the penguin's feet, it is just barely above freezing. It provides just enough oxygen and warmth to keep the tissue alive and prevent ice crystals from forming. But because the foot is basically the same temperature as the ice it's standing on, there is almost zero temperature gradient.
And no gradient means no heat loss to the environment. That is brilliant, built-in thermal recycling.
But even with that, a single penguin standing alone in a 300-kilometer-per-hour katabatic storm is gonna die.
Right. The physical body alone isn't enough. Which brings us to the huddle. And I gotta say, this isn't just a bunch of birds standing in a circle trying to stay warm. The sources show it is mathematically bizarre.
The emperor penguin huddle forces a complete reevaluation of the boundary between an individual and a collective. Thousands of these males form a dense, tightly packed mass, and the thermal dynamics are just extreme.
Like, how hot does it actually get?
Well, the outside air might be minus 60 degrees Celsius, but the temperature at the very center of the huddle, trapped by tens of thousands of penguin bodies, can reach nearly 37 degrees Celsius.
Which is like 98 degrees Fahrenheit?
Yes.
So it gets so hot in the middle of a deadly Antarctic winter that birds actually have to break the huddle just to cool down.
But the brilliance of the huddle is that it is never static. It is in a state of continuous slow-motion rotation. The birds on the freezing windward edge of the huddle don't stay there and freeze to death.
Right.
The entire mass slowly ripples and shifts. The birds on the outside gradually rotate along the flank and into the warm, protected center, while the birds in the center are slowly pushed toward the outer edge to take their turn shielding the colony.
Okay, wait. You're telling me thousands of penguins are shifting in the pitch dark, balancing fragile eggs on their feet, and there's no leader? That sounds like a recipe for a massive stampede. How do they not trample each other and crush thousands of eggs during this massive continuous rotation?
Physicists and mathematicians have actually modeled this. They use the same fluid dynamics principles used to study traffic jams and molecular movement.
Jig jams.
Yeah. There is no central coordination. The huddle operates purely as a decentralized system driven by individual thermal responses. It works on a threshold of proximity.
Break that down for me. How does a threshold of proximity make 10,000 birds rotate perfectly?
Well, imagine a single bird on the edge gets slightly too cold. To minimize its surface area exposed to the wind, it takes a tiny step, maybe just 2 inches, to close a gap between itself and the bird next to it.
Okay.
But penguins pack so tightly that this tiny movement disrupts the personal space of the neighboring bird. That bird is then forced to take a 2-inch step to maintain its own equilibrium.
It creates a physical pressure wave.
Exactly. That single 2-inch step cascades through the entire dense crowd as a wave of micro-adjustments. They aren't consciously planning the rotation of the huddle.
Right, they aren't thinking, time to rotate.
No, they're simply reacting to the temperature and pressure gradient immediately surrounding their own bodies. But those individual localized reactions magically generate a highly coordinated, life-saving collective behavior.
We're looking at a superorganism. The collective behaves as a single entity, just breathing, shifting, and distributing the suffering, so no single member carries a lethal burden. I mean, the sources point out that human engineers actually study these huddles.
They do, yeah.
They look at how penguins pack together and manage thermal dynamics to improve the insulation of our own buildings. And they literally use the math of those pressure waves to design better human crowd management and autonomous traffic algorithms.
Nature has been running optimization algorithms for hundreds of millions of years. We are merely analyzing the output at this point.
Right, so penguins survive by hoarding heat through community. But what happens if you can't rely on community? What if survival requires hoarding something even more immediate than heat, like oxygen?
Then you have to look just a few miles away.
Yeah, if we move just away from the penguin colonies to the edge of the ice, the survival strategy changes entirely.
We reach the ice line, the boundary where the solid sea ice meets the open ocean. In ecology, transitions between habitats, the edges, are always the most volatile, dangerous, and productive zones.
And the water beneath this sea ice sits at minus 1.8 degrees Celsius. That's about 28.7 degrees Fahrenheit. Now, fresh water freezes at 32 Fahrenheit. So this ocean water is literally colder than freezing, kept liquid entirely by its high salt content.
And this dark, sub-zero world is the domain of the weddell seal.
Yes, the weddell seal. They live further south than any other permanent mammalian resident on Earth, right?
They do. They spend the vast majority of their lives submerged in this black water beneath the ice.
And the dive profiles on these seals are just hard to fathom. They routinely dive for up to an hour at a time, reaching depths of over 600 meters.
Which is incredible.
To put that in perspective for you listening, human scuba divers run into serious physiological trouble like nitrogen narcosis, oxygen toxicity, at just 40 or 50 meters. These mammals are going down 600 meters and holding their breath for an hour. How does a mammalian cardiovascular system not just seize up and die under that pressure?
Well, the weddell seal has evolved a suite of physiological responses collectively known as the mammalian dive reflex, but they've taken it to an absolute extreme. When they dive, their body undergoes a heavily controlled shutdown.
A shutdown?
Yeah. The first step is a profound state of bradycardia. Their heart rate drops from a normal resting rate of maybe 60 or 70 beats per minute down to under 10 beats per minute, sometimes as few as 4 beats a minute.
Their heart just practically stops.
It slows to a crawl to conserve oxygen. Simultaneously, their circulatory system performs a massive triage. Blood vessels constrict, shutting off blood flow to the skin, the digestive organs, and the extremities.
Just completely cutting them off?
Yes. The seal hoards its oxygenated blood almost exclusively for the vital organs that absolutely require it to stave off death. So the brain, the heart, and the lungs.
But they're swimming. They're actively hunting fish at 600 meters deep. You can't swim if your muscles aren't getting any oxygen from your blood.
And this is where their biochemistry solves the problem that the circulatory system just created. Their muscles are packed with an iron and oxygen-binding protein called myoglobin.
Myoglobin, okay.
Now, you have myoglobin in your muscles too, but weddell seals have it in such incredibly high concentrations that it changes the physical color of their tissue. Their muscles appear nearly black.
Black muscles acting as localized oxygen tanks.
Precisely. The myoglobin stores oxygen directly within the muscle tissue. So even when the blood supply is completely cut off by that dive reflex, the muscles can continue to fire, contract, and operate for an hour, just burning through their own internal, localized reservoirs of oxygen.
Okay, so that explains how they hold their breath. But getting back up is the real nightmare, because they are hunting under a solid ceiling of ice that can stretch for miles. They can't just float up to the surface anywhere they want.
No, they rely on maintaining a network of breathing holes in the ice. And throughout the winter, as new ice forms and tries to seal them in, weddell seals literally use their teeth to scrape away the freezing water.
Their teeth?
Yeah, they act as biological ice augers, grinding their teeth against the ice over and over just to maintain a tiny borehole to the surface.
The toll that must take on their teeth.
It is severe.
Yeah.
Dental wear is actually a primary cause of mortality for older seals. Once their teeth wear down to the nerve, they can no longer maintain their breathing holes and they drown. It is their only lifeline.
But imagine being down there. You are 600 meters deep. You've been swimming for 50 minutes. It is pitch black. How do you find a hole in the ice that's only 2 feet wide? I mean, I liken it to an astronaut on a spacewalk whose tether snaps.
That's a terrifying analogy, but accurate.
You have to find the airlock, this tiny door on the side of a massive space station, purely from memory, before your oxygen runs out.
And the spacewalk analogy perfectly captures the stakes here.
Yeah.
Researchers have discovered that weddell seals rely on extraordinarily complex spatial mapping and acoustic memory.
Acoustic memory. So they're listening to the ice.
Well, the ice isn't silent, right? It cracks, it groans, and it shifts. And the seals themselves emit a wide array of vocalizations. Trills, chirps, low-frequency pulses.
Like echolocation.
Similar. They use the acoustic properties of the underwater environment, the way sound bounces off the under-ice topography, to map the geographic layout of the ceiling above them. They can navigate back to a single, narrow hole from hundreds of meters away in near total darkness without ever surfacing to check their bearings.
They are essentially doing under-ice cartography. They are maintaining mental models of a dynamic environment.
Exactly.
And they have to be constantly aware because the ice edge isn't just a place to breathe. It is a hunting ground, and it is a battleground. If you are a penguin, eventually you have to cross that ice line to get into the water to feed, and waiting for you is the leopard seal.
The leopard seal is an apex predator perfectly adapted to this transition zone. They are massive, up to 3.5 meters long, with an incredibly powerful, almost reptilian physiology. But their success isn't just about speed, it is about calculated timing and ecological exploitation.
They exploit the edge.
Exactly. A penguin standing on the edge of the ice knows there might be danger in the water, so it hesitates, it paces, it waits.
Nobody wants to go first.
And the leopard seal understands this hesitation. It doesn't waste energy patrolling randomly. It waits out of sight, right at the boundary, for that exact moment of forced commitment when the penguin finally dives. It exploits the psychological necessity of its prey.
That's chilling. But the predation at the edge gets even more sophisticated than ambush tactics. We have to talk about the orcas, the killer whales, because the research details a hunting technique that is equal parts terrifying and brilliant.
Wave washing. It is a masterclass in weaponizing fluid dynamics.
Right, so paint the picture for us.
Yeah.
A seal is resting on a chunk of floating sea ice, an ice floe. It thinks it's safe because it's physically out of the water, but a pod of orcas spots it. And they don't just jump up and try to grab it, right?
No, they coordinate a physical manipulation of their environment. The pod will line up side by side, perfectly synchronized. They swim at high speed directly toward the ice floe, and at the last possible second, they dive beneath it, using the displacement of their massive bodies to generate a massive, unified wave.
They act as a biological wave machine.
This wave washes directly over the ice floe. It either shatters the ice completely or creates enough lateral force to simply sweep the seal off the ice and into the waiting mouths of the rest of the pod on the other side.
But here's the thing that really elevates this from just animal instinct to something entirely different in my mind. This isn't a behavior shared by all orcas globally. An orca in the Pacific Northwest doesn't know how to do this. This specific wave-washing technique is unique to certain pods in the Antarctic.
It is a localized, multi-generational hunting strategy. It is not coded in their DNA, it is learned. Yes, adult orcas have been heavily documented teaching this exact technique to younger members of the pod. They will coordinate a wave, wash a seal off the ice, and then instead of killing it, they will gently pick the seal up, put it back on the ice, and force the juvenile orcas to practice making the wave themselves.
They are holding tactical classes in fluid dynamics. They are using a live seal as a training dummy. I mean, if a pod of orcas is passing down highly specific, localized wave-making techniques to their offspring, doesn't that fundamentally prove that culture, the passing down of learned traditions, isn't exclusively human?
It absolutely proves it. The scientific consensus is increasingly recognizing these highly specific, localized behaviors as distinct animal cultures. The Antarctic is a cultural transmission zone for highly intelligent, highly social predators.
It's just incredible. But all of these animals, the penguins, the seals, the orcas, no matter how intelligent they are still tethered to the surface. They breathe air. So let's cut that tether. Let's transition from animals holding their breath to creatures that have fundamentally altered their own blood to survive the freezing depths.
Now we descend into the water column. This is where we encounter the notothenioidae, commonly known as ice fish, and the eelpouts. These families of fish absolutely dominate the biomass of the Southern Ocean.
And the water they live in is still that minus 1.8 degrees Celsius.
Yeah.
If you drop a normal fish into that water, the water molecules inside the fish's blood and cells will physically crystallize.
Right. The ice lattices expand, puncture the cell membranes, and the fish dies instantly.
So how are the ice fish just casually swimming around in it?
They survive because they have evolved a biochemical defense mechanism that is functionally miraculous. Antifreeze glycoproteins.
Antifreeze. I know what antifreeze does in a car radiator. It lowers the freezing point of the liquid. Is it doing the exact same thing in the blood?
The end result is similar, but the biological mechanism is far more elegant and targeted. These glycoproteins circulate continuously in the blood and bodily fluids of the ice fish. In water, that cold microscopic ice crystals inevitably begin to form inside the fish's body.
That sounds bad.
It would be.
Yeah.
But before those crystals can grow and expand into deadly lattices, the glycoproteins intercept them.
How do they intercept them?
Through chemical binding. The structure of the glycoprotein is perfectly shaped to match the atomic spacing on the growth surface of an ice crystal. The proteins physically lock onto the edges of the tiny ice crystal via hydrogen bonding. Once the proteins are attached, they block other water molecules from joining the crystal lattice.
Oh, wow. So they put a microscopic molecular straitjacket on the ice crystal so it can't grow.
Precisely. The ice crystals are arrested in their microscopic state. They can't grow, they can't puncture cells, and the blood remains entirely fluid even when the ambient temperature is well below the freezing point of normal vertebrate blood.
That is biological alchemy. But there is a specific family of ice fish, the Channichthyeidae, the crocodile ice fish, that takes this extreme adaptation and adds a modification that sounds like an evolutionary glitch.
Yes.
They have completely lost their red blood cells.
They're the only known vertebrates on the entire planet that lack red blood cells and lack hemoglobin.
And hemoglobin is the protein complex that makes blood red, right? It binds to oxygen in the lungs or gills and carries it through the body. It is the primary oxygen transport mechanism in every vertebrate. So if you cut open a crocodile ice fish, what does its blood look like?
It runs completely clear. It looks like water or slightly cloudy yellowish plasma.
I'm trying to visualize how this works. Think about a city's transport system. Normally, you have dedicated cargo trucks, the red blood cells, picking up packages of oxygen and delivering them with high efficiency all over the city. The ice fish has essentially fired all the cargo trucks, and now they just have a massive, slow-moving river of fluid, hoping the packages of oxygen just float to where they need to go. How does a complex animal survive without a dedicated transport mechanism?
Your river analogy is perfect, but it only works because of a physical paradox regarding freezing water. We view extreme cold as purely hostile, but cold water has an incredible physical property. It holds vastly more dissolved gas than warm water. The Southern Ocean is hyper-oxygenated.
The environment is just flooded with oxygen.
Exactly. Because the water is so saturated with oxygen, the ice fish can simply absorb it. They absorb oxygen directly from the water through their skin, which is completely scaleless and heavily vascularized, and that oxygen dissolves straight into their clear blood plasma.
But blood plasma alone is a terrible carrier of oxygen compared to hemoglobin. It's incredibly inefficient.
It is terribly inefficient. To compensate for this massive physiological downgrade, the ice fish had to evolve a suite of extreme anatomical workarounds. Because the plasma carries so little oxygen, they have to pump a massive amount of it to keep their tissues alive. Consequently, they have enormously enlarged hearts, several times larger than a similar-sized normal fish.
So they have giant hearts.
Giant hearts. And to make pumping all that fluid easier, their blood vessels are incredibly wide to reduce cardiovascular resistance. They also have a huge total volume of blood plasma.
They pump a massive volume of clear fluid through giant veins using a massive heart, just to move enough passively dissolved oxygen to survive. But from an evolutionary standpoint, this sounds like a disaster. Evolution doesn't happen overnight. There had to be an awkward transitional phase millions of years ago where the ancestor of this fish suffered a genetic mutation, losing its hemoglobin, but it hadn't yet evolved the giant heart and the wide vessels. In any normal environment, a fish that suddenly loses its red blood cells just dies. How did nature allow for such a risky beta test?
This is one of the most fascinating debates in evolutionary biology right now. The prevailing consensus is exactly as you pointed out. The loss of hemoglobin wasn't a deliberate adaptation to the cold. It was an accident. It was a random genetic deletion. In any other ocean on Earth, that mutation is instantly lethal. But in the hyper-oxygenated freezing waters of the Antarctic, the environment provided a unique safety net.
The water had so much oxygen that the fish didn't immediately suffocate.
Exactly. The extreme environment was permissive. It allowed these mutant, anemic fish to survive just barely long enough to reproduce. Over millions of subsequent years, compensatory mutations, the larger heart, the wider vessels, the scaleless skin, were naturally selected for because they helped this weird, clear-blooded fish survive better. It's a testament to how extreme environments can warp the trajectory of evolution.
It's like jumping out of an airplane without a parachute, but discovering that the air density below you is exactly thick enough to let you survive the fall while you frantically knit a parachute on the way down.
That captures the evolutionary precariousness perfectly.
So we have clear blood in the water column. But let's dive even deeper. Let's go to the bottom, the seafloor, the benthic zone. Because conventional logic says the deeper you go into freezing dark water, the less life you'll find. But the research completely upends that assumption.
The benthic communities on the Antarctic seafloor are shockingly diverse and densely packed. It is not a barren wasteland down there. Researchers have documented up to 155,000 individual animals inhabiting a single square meter of the seafloor in certain productive areas.
155,000 animals in 1 square meter. That's the size of a kitchen table.
Now, a vast majority of those are microscopic or very small invertebrates, amphipods, nematodes, and the like. But amidst that microscopic density, we also see the total opposite end of the spectrum, the phenomenon of polar gigantism.
The giants of the deep. Let's talk about the sea spiders.
Pycnogonids. In warmer oceans globally, sea spiders are tiny cryptic creatures, often the size of a fingernail or a coin. But on the Antarctic seafloor, they grow to monstrous proportions. They have leg spans reaching up to half a meter, about the size of a large dinner plate.
A dinner plate-sized spider crawling on the bottom of the ocean. Nope. And they are alone. We have giant isopods, which are essentially underwater pill bugs like Glyptonotus antarcticus, weighing up to 70 grams. We've got the colossal squid, which can grow up to 14 meters long and possesses the largest eyes in the animal kingdom. And then there are the sponges.
The Anoxicalix jubini, sometimes referred to as the giant volcano sponge. These are massive, structure-forming organisms on the seafloor, somewhat resembling giant pale vases. They can reach 2 meters in height.
And their lifespans defy our understanding of biological time.
When scientists first started observing these sponges, they would measure them, come back a decade later, and record 0 perceptible growth. This incredibly slow metabolic rate suggested they were incredibly ancient. Some initial estimates place the age of certain large individuals at 10 to 15,000 years old.
15,000 years old.
Making them potentially some of the longest-lived organisms on the planet. Though interestingly, longer-term studies have shown their growth can be highly variable. They might remain entirely stagnant for decades, and then suddenly, perhaps triggered by a specific influx of nutrients, expand rapidly. But they operate on a timescale that is vastly different from ours.
But let's go back to the physics of gigantism. Why? Why does freezing dark water make bugs grow to the size of dinner plates? Is it just a lack of predators?
Predators play a role. But the primary driver loops right back to the oxygen paradox we discussed with the clear-blooded icefish. Cold water holds more oxygen. Many of these benthic creatures, like the giant sea spiders, don't have lungs or gills. They breathe passively by absorbing oxygen directly across the surface of their exoskeleton into their bodily fluids.
And this runs into a hard physical limit, the square-cube law in physics.
Exactly. As any three-dimensional shape grows larger, its internal volume increases exponentially faster than its exterior surface area. In warm water, where oxygen is less concentrated, a sea spider has to stay small. If it grew too large, it would have too much internal volume and not enough exterior skin surface area to absorb the oxygen required to keep that massive body alive. It would suffocate from the inside out.
But in Antarctica,
the water is so heavily saturated with oxygen that this physical limit is pushed drastically outward. The concentration gradient is so high that oxygen easily diffuses deeply into their tissues. This allows their passive breathing mechanism to support a vastly larger body mass. Combine that abundant oxygen with a severely lowered metabolic rate due to the cold, meaning they burn energy incredibly slowly. And you have the perfect biochemical recipe for slow, continuous growth over incredibly long lifespans.
so they live in a world where everything operates in slow motion, they breathe through their skin, and they grow into giants simply because the physics of the water allows it.
They exist on an entirely different metabolic clock than the rest of the biosphere.
We've gone deep into the freezing ocean, but what happens when we leave the water entirely? If you think giant slow-motion spiders and clear-blooded fish are strange, the research takes us to a place that makes the bottom of the ocean look lush and accommodating. We're moving from the deep water to dry, frozen rock.
We are entering the McMurdo Dry Valleys. This is the absolute limit of terrestrial habitability.
I had no idea a place like this even existed on Earth. When we think of Antarctica, we think of endless ice sheets. But the dry valleys have no ice sheet. There is no snow. It is just bare, freezing, scouring rock. Why is there no ice?
It's due to a combination of geography and atmospheric physics. The Transantarctic Mountains physically block the ice sheet from flowing into these specific valleys. And the katabatic winds we mentioned earlier, those dense, heavy winds accelerating down the mountains, they heat up just slightly as they compress, and they become incredibly dry. As they blast through the valleys, they instantly evaporate any moisture, snow, or ice that might happen to fall.
The research estimates that in some parts of these valleys, no rain or snow has fallen for nearly 2 million years. It is so utterly desolate, so devoid of moisture, that NASA uses it to test their Mars rovers. It is the closest earthly analog to the Martian surface.
By all conventional biological definitions, the dry valley should be entirely sterile. The extreme cold, the profound desiccation, and the incredibly high UV radiation unmitigated by any atmospheric moisture should destroy all cellular life. And yet life found a way. But to survive, it had to retreat.
Retreat where? There's no soil, it's just solid rock.
It retreated inside the rocks themselves. Biologists have discovered what are known as crypto-endolithic communities. Crypto meaning hidden, endo meaning inside, and lithic meaning stone. These are complex, interdependent communities of fungi, algae, and bacteria living literally millimeters beneath the surface of translucent sandstone rocks.
They live inside solid stone.
The physical structure of the sandstone provides a microscopic sanctuary. The rock acts as a physical shield against the scouring winds, the UV radiation, and the extreme freeze-thaw cycles on the surface. But because sandstone is slightly translucent, it allows just enough photons of sunlight to penetrate a few millimeters deep. This allows the algae to photosynthesize and produce food. Meanwhile, the fungi wrap around the algae, providing a structural matrix and retaining whatever microscopic trace amounts of moisture might condense inside the rock pores.
It's a complete self-sustaining microecosystem squeezed into a paper-thin layer inside a solid rock, surviving a 2 million year drought. But the rocks aren't the only place hiding microscopic masters of survival. Let's talk about the creatures hiding in the tiny patches of moss and lichen, the tardigrades, the water bears.
Tardigrades are microscopic invertebrates, famously resilient, and they possess a biological superpower called cryptobiosis. Specifically, anhydrobiosis, the ability to survive extreme dehydration.
Break down the mechanics of cryptobiosis for us, because what they do sounds less like biology and more like magic.
When conditions in the Antarctic become untenable, when the temperature drops too far, or crucially, when the microscopic film of water they live in dries up, the tardigrade enters a state called a tun. It begins a highly coordinated structural and chemical transformation. It physically pulls its 8 legs inside its body, shrinking into a tight microscopic barrel shape to minimize surface area.
And then it gets rid of its water.
This is the critical step. Normally, if a cell freezes, the water inside expands into ice crystals, which act like microscopic knives that shred the cell membrane from the inside out. To prevent this, the tardigrade expels almost all of the water from its body. But a cell without water collapses and dies. So the tardigrade synthesizes massive amounts of specialized molecules, most notably a sugar called trehalose and certain intrinsically disordered proteins.
What does the sugar do?
The trehalose and these proteins essentially replace the water molecules. They form a glassy matrix inside the cell that structurally props up the cell membranes and protects the DNA and vital proteins from unwinding or shattering. The tardigrade effectively turns its internal biology into biological glass.
It freeze dries and vitrifies itself.
Exactly. And in this tun state, its metabolic rate drops to less than 0.01% of normal. It is virtually undetectable. The biological clock stops. In this state of suspended animation, they can survive being frozen in solid ice for decades. They can survive blasts of radiation that would instantly kill a human. They can even survive being exposed to the vacuum of space. And when conditions finally improve, when a drop of water returns, they rehydrate, the sugar matrix dissolves, they unfurl their legs, and they simply walk away as if nothing happened.
It's exactly like a perfectly compressed zip file on a computer. You can put a zip file on a hard drive, toss it in a drawer for a century, expose it to magnetic fields, drop it on the floor. As long as the core code, the vitrified matrix, is intact, when you finally plug it in and click unzip 100 years later, the file opens perfectly and runs like it was created yesterday.
They are biologically archiving themselves.
But this introduces a profound philosophical and biological question regarding time. If a tardigrade can pause its metabolism indefinitely, does it actually age while it's in the tun state? Think about it. If a tardigrade is born, lives actively for 1 month, enters the tun state and freezes for 100 years, and then wakes up and lives for another month, did it live for 2 months or did it live for 100 years in 2 months? What is its actual age?
This forces us to decouple chronological time from biological time. Biologically speaking, aging or senescence is defined by the accumulation of cellular damage, DNA degradation, and metabolic byproducts over time. Because metabolism is essentially halted during cryptobiosis, and the cellular structures are perfectly preserved by the trehalose matrix, the biological clock does not tick. Experientially and cellularly, the tardigrade only lived and aged for 2 months. Chronologically, it existed on Earth for a century.
That completely breaks our human perception of a continuous lifespan. And speaking of breaking our perception of time, the dry valleys aren't the only place hiding ancient suspended secrets. We need to look at what lies beneath the ice sheet itself, the subglacial lakes.
This is one of the most exciting and heavily debated frontiers in modern Earth science. Beneath the 4-kilometer-thick Antarctic ice sheet, radar has revealed a vast interconnected network of liquid water lakes.
How can there be liquid water under 4 miles of freezing ice?
2 reasons. First, the immense crushing pressure of 4 kilometers of ice physically lowers the melting point of water at the bottom. Second, the ice sheet acts as a massive insulating blanket, trapping the geothermal heat radiating up from the Earth's crust. This combination of pressure and geothermal heat keeps these lakes liquid.
And the largest of these is Lake Vostok.
Yes. Lake Vostok is roughly the size of Lake Ontario, and it has been sealed beneath the ice in total absolute darkness, completely isolated from the Earth's atmosphere for an estimated 1 million to 15 million years.
Sealed for 1 million years. No sunlight, no fresh air, utter isolation. And yet, research teams who have sampled the water from these subglacial environments have found genetic traces of microbial life. How is life surviving for 1 million years without the sun?
They cannot rely on photosynthesis. There are 0 photons down there. Instead, they rely on chemosynthesis. They extract the energy they need to survive from chemical reactions involving the minerals crushed in the rock bed of the lake and the water itself. It is a completely alien, dark food web, utterly disconnected from the solar energy that powers 99% of the rest of life on Earth.
But wait, we have to address the obvious logistical nightmare here. You have a lake sealed for 1 million years. To sample it, scientists have to drill a hole through 4 kilometers of ice using massive industrial equipment. How can they be absolutely sure they aren't just contaminating this pristine million-year-old lake with modern surface bacteria hitchhiking on their own drill bit? If you find a microbe, how do you know you didn't just put it there?
Contamination is the single greatest challenge in subglacial research. It is a point of massive scientific contention, and the protocols developed to prevent it are extreme. They use hot water drilling techniques rather than mechanical bits. The water used for drilling is filtered, exposed to massive doses of UV radiation, and treated with hydrogen peroxide. Furthermore, they use carefully controlled pressure differentials. When the drill finally breaches the surface of the subglacial lake, the pressure inside the borehole is kept lower than the pressure in the lake.
So the lake water physically rushes up into the borehole, preventing the drilling fluid from falling down into the lake.
Exactly. The lake water rushes up, instantly freezes into a plug, and then they extract that newly frozen plug of lake water to analyze it, ensuring the lake itself remains untouched. Despite these extreme measures, skepticism is healthy and necessary. Every claim of subglacial life is heavily scrutinized to rule out contamination. But as more subglacial lakes like Lake Mercer and Lake Whillans are sampled using these ultra-clean protocols, the scientific consensus is solidifying that endogenous chemosynthetic microbial communities do, in fact, exist down there.
If they do exist, the implications are staggering, not just for Antarctica, but for the universe.
The implications for astrobiology are massive. Antarctica subglacial lakes are our best terrestrial analog for the icy moons of the outer solar system.
Europa, Jupiter's moon, or Enceladus, Saturn's moon.
Exactly. Both are covered in miles of solid ice with liquid oceans beneath, kept warm by tidal friction. If microbes can survive for millions of years in a dark, sealed, freezing lake under the ice of Antarctica via geothermal chemistry, there's absolutely no biological reason a similar mechanism couldn't support life under the ice of Europa. It proves that the habitable zone of a solar system isn't just about proximity to a sun for liquid surface water. Life can persist in the dark, driven entirely by geological chemistry.
We've gone from emperor penguins sharing heat through decentralized algorithms, to weddell seals mapping the underice acoustics, to clear-blooded giants running on passive oxygen, to microscopic tardigrades time-traveling through cryptobiosis. But all of this entire hidden, frozen, slow-motion world of survival is just waiting, because something massive is about to happen.
The seasonal window. The return of the sun.
This entire deep dive has been focused on the dark and the cold. But when the light finally breaks over the horizon, it's like a starting pistol for the entire continent. The transition is explosive.
The return of the sun doesn't immediately bring atmospheric warmth, but it brings photons. As the sea ice begins to thin and fracture, those photons penetrate into the water column, and they hit the microscopic life that has been lying dormant in the ice all winter. This triggers a massive, explosive bloom of phytoplankton and ice algae. Microscopic plants multiplying by the trillions, turning the water green and brown.
And that immense algal bloom acts as the dinner bell for the arrival of the most important animal in the entire Antarctic ecosystem, the keystone species.
The Antarctic krill. Euphausia superba.
The numbers regarding krill are almost impossible to comprehend. We're talking about a total biomass of roughly 500 million tons.
To put that immense figure in perspective, if you took the total weight of all 8 billion humans on Earth, the krill in the Southern Ocean outweigh us. There's more krill biomass than human biomass.
And they gather in swarms that stretch for kilometers. The density can reach up to 30,000 individual krill in a single cubic meter of water. The swarms are so unbelievably dense, they literally turn the ocean water red. They are the biological engine of the ocean. They gorge on the phytoplankton, converting that solar energy into protein, and then absolutely everything else in the ocean eats the krill.
But krill have their own extreme adaptations. We have to consider how they survive the dark winter when there is no sun and no phytoplankton to eat. They don't simply hibernate.
Right, this detail blew my mind. When food is scarce during the dark winter, adult Antarctic krill can actually revert to a juvenile stage. They undergo molts where they physically shrink in size, essentially consuming their own body mass autophagy to survive starvation until the sun returns. They age backward and shrink to survive.
It is a radical metabolic strategy. But when summer is booming and the algae is thick and the krill are swarming in those massive red clouds, the sheer density of this food source triggers one of the greatest biological events on Earth. The arrival of the giants.
The great whales. Blue whales, humpback whales, fin whales. They migrate thousands and thousands of miles from tropical and temperate waters across the globe just to reach the Southern Ocean during this specific brief summer window. Why undertake that massive migration? Why swim across the globe?
Because of the physics of lunge feeding and the absolute necessity of density. This ecosystem is built on a profound paradox. The largest animals to ever exist on Earth are entirely dependent on some of the smallest.
Explain the physics of lunge feeding. Why is it so demanding?
A blue whale feeds by accelerating to high speed, opening its massive mouth and expanding the pleated grooves on its throat. It engulfs an enormous volume of water and krill, a volume of water that can weigh as much as the whale itself. The sheer drag of taking in that much water halts the whale's forward momentum almost instantly. Then it has to use massive muscular effort to push all that water out through its baleen plates, trapping the krill inside.
Accelerating a 100-ton body, opening a giant parachute underwater, coming to a dead stop, and then pushing a swimming pool's worth of water out of your mouth. The kinetic energy required to do that must be astronomical.
It is extremely energetically costly. The math of survival here is brutal. If a whale expends the energy to lunge, but only catches a few sparse krill, it operates at a massive net energy loss. If it does that repeatedly, it will literally starve to death while eating. Therefore, survival for these whales isn't about simply finding food. It is about finding absolute density. They must locate swarms where the krill are packed so tightly that a single exhausting lunge provides a caloric surplus massive enough to offset the cost of the lunge itself.
Antarctica in the summer is one of the only places on the planet that offers that kind of extreme prey density. The way I visualize this entire system is like a gigantic biological battery. The Southern Ocean charges up this battery all winter and spring with nutrients, and then the sun hits the algae, the krill explode, and the battery is fully charged. Then the whales, these massive, majestic machines, arrive. They plug into the battery. They charge up their immense bodies with millions of calories of krill fat.
And then, when the summer season ends and the ice begins to return, the whales migrate away.
Exactly. They leave, and as they travel thousands of miles to breed in warmer, nutrient-core waters, they distribute that Antarctic energy across the entire planet. They're literally powering the global ocean with the energy they harvested from the ice.
The biological term is nutrient vectors. They are the transport mechanism for the immense productivity of the Southern Ocean.
And it's not just the deep ocean that operates on this rhythm. The air above the ocean is part of it too, the albatrosses.
The aerial masters of the Southern Ocean.
We talked earlier about the katabatic wind, those deadly 300-kilometer-per-hour storms that force the penguins to huddle. The albatrosses don't hide from those winds. They use them. They use the air currents as a physical habitat.
They utilize a flight technique called dynamic soaring. It's a method of extracting energy directly from the wind gradients over the waves. The wind speed is slower right at the surface of the wave due to friction, and faster just a few meters higher up. The albatross dives down into the slow air, turns, and uses its massive wingspan to pop up into the fast-moving air, which instantly accelerates the bird. It then glides forward, drops back down, and repeats the cycle.
They are essentially surfing the boundary layer of the wind. They can travel thousands of kilometers foraging for food, circling the entire globe without barely flapping their wings. They harness the most destructive weather on Earth for free transportation.
It is a perfect evolutionary synergy with the environment.
But looking at this entire intricate system, I have to ask about the fragility of it all. Because everything we've just discussed, the photons hitting the water, the phytoplankton blooming, the krill swarming, the whales arriving, the penguins timing their chicks to hatch exactly as the ice breaks up, it all feels so precarious. If the sun acts as the starting pistol, but the sea ice doesn't melt in the right way, or it melts too fast, or the algae blooms 2 weeks late, does the whole synchronized race just collapse?
You've identified the critical vulnerability of the Antarctic rhythm. It is a highly synchronized, exquisitely delicate system that evolved over millions of years of relative stability. It has a very low tolerance for dissonance. If sea ice coverage drops early, there is less physical habitat for the ice algae to grow on. Less algae means fewer juvenile krill survive the winter. A delay of just a few weeks in the algae bloom can mean that penguin chicks hatch, but the parents can't find food fast enough in the ocean, leading to massive colony failures. A poor krill year can derail the breeding success of whales that migrated thousands of miles expecting a caloric surplus. The timing must be perfect.
And that vulnerability is exactly why the rhythm of the sun and the ice, which has persisted for millennia, is now facing a disruption that it simply did not evolve to handle. Novel, rapid changes introduced by humans.
The conservation and human impact aspect to the data is sobering. Antarctica is geographically isolated, surrounded by the fierce circulating currents of the Southern Ocean. For millions of years, this physical isolation acted as a fortress, but it also means that the wildlife there evolved without certain environmental pressures, making them uniquely, devastatingly vulnerable to new threats.
Evolutionary naivety. If you evolve on an isolated island with no land predators, you don't evolve defenses against land predators. A penguin has no fear of something walking up to it on land because, historically, nothing dangerous ever walked up to it on land. And then humans arrived. The whalers and sealers arriving over the last 2 centuries didn't just bring harpoons, they brought stowaways.
Introduced species, specifically rats, mice, and on some subantarctic islands, cats, pigs, and reindeer. To a ground-nesting seabird like an albatross or a petrel that has never encountered a mammalian predator, the introduction of a nest-raiding rat is catastrophic. The birds have no instinct to defend their nests from them. Rats eat the eggs and the chicks, entirely decimating local bird populations in a matter of seasons.
And we can't ignore the direct historical exploitation. The history of whaling and sealing in the Southern Ocean left horrific scars on the populations. Species like the blue whale were hunted to the absolute brink of extinction before international protections kicked in.
While large-scale commercial whaling has largely ceased, the modern threats are perhaps more insidious because they are systemic. Climate change is altering the extent and duration of the sea ice, which, as we just discussed, threatens the entire physical foundation of the krill-based food web. Furthermore, as the oceans absorb more carbon dioxide from the atmosphere, it leads to ocean acidification.
The chemistry of the water is changing.
Yes. The increased acidity reduces the availability of carbonate ions in the water. Countless tiny organisms at the base of the food web, like pteropod sea butterflies, need those carbonate ions to build their calcium carbonate shells. If the water becomes too acidic, their shells literally begin to dissolve. If the base of the food web dissolves, the entire tower collapses.
And commercial fishing hasn't left the Southern Ocean. We discussed the ice fish earlier. The research highlights the intense commercial fishing of the Patagonian and Antarctic toothfish, which are marketed in restaurants as Chilean sea bass. The problem is that illegal, unreported, and unregulated fishing is rampant.
The toothfish is a perfect example of why Antarctic species are so mathematically vulnerable to exploitation. The evolutionary traits that make them marvels of survival, their incredibly slow metabolic rate, their slow growth, their extremely late onset of sexual maturity, are exactly what make them completely incompatible with industrial fishing.
The math doesn't work.
It doesn't. If you pull a 10-year-old fish out of a warm, fast-paced ocean ecosystem, that fish may have already reproduced 5 times, replacing itself in the population. If you pull a toothfish out of the freezing Antarctic waters, it might not even reach sexual maturity until it is 15 years old. You are removing a fish before it has reproduced even once. The population simply cannot repopulate fast enough to offset the harvest.
And it's not just the fish they are catching. The illegal longline fishing industry causes devastating bycatch. They string out fishing lines that are miles long, studded with thousands of baited hooks. Albatrosses, using that dynamic soaring we talked about to scour the ocean for food, swoop down to grab the bait as the lines are being set. They get hooked, they are dragged underwater, and they drown. It's an agonizing waste.
To mitigate these overlapping threats, there's a complex international framework of protection. The Antarctic Treaty System designates the entire continent as a natural reserve dedicated to peace and science, banning military activity and resource extraction on the land. And the Convention for the Conservation of Antarctic Marine Living Resources, or CCAM-LR, attempts to regulate human activity and fishing in the surrounding waters using an ecosystem-based approach.
Looking at this impartially, breaking down all the biological and conservation data we've discussed today, it strikes me that we are dealing with a system that is infinitely robust against extreme natural elements, but completely structurally defenseless against rapid, novel changes. I look at the Antarctic ecosystem like a highly optimized, custom-built piece of software running on a very specific, isolated piece of hardware. It runs flawlessly. The code of the krill, the algorithms of the penguins, the processor speed of the ice fish, it is all perfectly integrated. But if you introduce a single line of novel, incompatible code like an invasive rat, or a sudden change in ocean pH, or an illegal fishing net, the software doesn't know how to process it. It wasn't built to handle external operating systems. The whole program crashes.
That is a highly accurate way to frame it. The evolutionary isolation that allowed for these incredible specializations is the exact same mechanism that ensures their vulnerability in a rapidly connecting, rapidly warming world.
We have covered massive ground today. We've taken a deep dive through a stack of sources that fundamentally reshape how we see the bottom of the world. We've moved from the surface of the ice, unpacking the thermodynamic physics of emperor penguins forming decentralized superorganism huddles to survive lethal storms.
We descended to the perilous ice line, where weddell seals shut down their organs and rely on black, myoglobin-rich muscles and acoustic memory to navigate pitch-black labyrinths. We saw predators like leopard seals exploiting psychological hesitation and wave-washing orcas demonstrating localized, generational cultural transmission that rivals our own.
We dove into the freezing dark water to find Channictheidae crocodile icefish running a biological transport system with clear blood and massive hearts, absorbing oxygen like a sponge. We explored the physics of polar gigantism, where sea spiders breathe through their skin and grow to the size of dinner plates simply because the hyper-oxygenated water allows it.
We ventured into the absolute extremes of the dry valleys, exploring the microscopic masters of time tardigrades, turning their biology into glass to hit pause on their own mortality. We discussed ancient microbes surviving on crushed rock in subglacial lakes, sealed under 4 kilometers of ice for 1 million years, redefining the parameters of astrobiology.
And finally, we saw how this entire intricate, slow-motion world is powered by the precise rhythm of the sun. The blooming phytoplankton, the swarming krill shrinking to survive the winter, and the delicate, high-stakes dance of giants like the blue whale pulling massive caloric surplus out of the ice to power the global ocean. Antarctica isn't an empty, barren desert. It is a masterpiece of biological engineering, a world of edges, and life balances perfectly on every single one of them.
But before we conclude, there's one final, mind-bending idea to consider, something that builds on everything we've discussed regarding extreme survival.
Think about the cryptobiosis of the tardigrades. Think about those chemosynthetic microbes deep in the sandstone, or the bacteria sealed in Lake Vostok for millions of years. Organisms that can effectively halt their own cellular degradation, existing entirely disconnected from the surface and the sun.
It forces us to drastically reconsider the timeline of life on our planet and what it truly means to be ancient.
If an organism can pause its biological clock indefinitely, what does that mean for the true timeline of life on Earth? Could it be possible that the absolute oldest living viable creature on our planet is not a giant redwood tree in California, and it's not a 15,000-year-old volcano sponge on the Antarctic seafloor? Could the oldest living thing on Earth be a microscopic organism frozen in a state of suspended animation in the Antarctic ice right now, just waiting for the right moment, maybe a moment thousands of years in the future, to finally thaw out and wake up?
It is a profound mystery, locked away in the ice.
Thank you for joining us on this deep dive into the extremes of biology. We hope it broke some of your expectations and showed you a world much richer, weirder, and more sophisticated than you ever imagined. Stay curious, keep questioning the maps, and keep exploring the incredible world around you.
Until next time.